In this chapter, we're going to be looking at some functions that are both exponential and logarithmic, and we're starting today with just the exponential, and even then we're focusing just on graphing them by hand as we're looking at how we would graph them by analyzing their transformations. So we'll have a few examples of that sort. So the book happens to use a as the base, right? So there's your a, there's your exponent. The exponent is the input. Now this works as long as our base is positive, and it works as long as our base doesn't equal 1. And we'll talk in more details about that a little bit later on and in the next section of notes. But in general, we're starting off with these limitations, and there's your base of A. However, we're graphing with transformations, and sometimes we have a negative sign in front, but the base still has to be positive. So even though our book uses the letter A to represent the base, I prefer to use the letter B to represent the base, and the reason is because we can then use A as a placeholder in front. That's your multiplier. So this A would represent your vertical stretch or shrink, or it could be the location of the negative. That way we can still have a positive base, and we just put the negative sign here. We park it in front as a separate factor. And that's more typical of what we've done with transformations in the past. We've always used A for the stretch or shrink, or the location of the negative sign. And if we're putting A to represent the base, well, then it might be confusing to represent a negative as an A. Wait, no, the A is the base? What's going on here? So in these examples and in the notes here, you're going to see that we're using B for the base, and that A is the multiplier in front, which is your vertical stretch or shrink, or even the location of a negative sign. We'll see some examples where we do just that. All right, so keep that in mind. So again, the book uses A as the base. So here they're graphing any base to the power of x, and what we observe is that it is increasing, right? We call that exponential growth. The domain is what can you plug in for x? What kind of exponent can you have? You can have a negative exponent or a positive exponent, so that's all real numbers. But notice your range is very limited. Your output, your y-coordinates are only above 0, and that means we have a horizontal asymptote here at 0. So it's not graphed in, but I'm going to represent that here now. That's the barrier. So this graph increases upwards from that. So this is a critical point. You have 0, 1. Right? Think about that. If you plugged in 0 as your input for x, any base to the power of 0 gives you an output of 1. So that's why 0, 1 is a critical point. We'll use one more. Let's plug in 1. What happens now? So if I plug in 1, any number to the power of 1 is just that number. Again, here we're using the letter A. I'm being consistent with what the book is using, so this is your base here. That's what we're trying to show. But for the transformations, we'll use the B for the base. And then notice that in this case over here, what's happening, it's really tiny print, it's hard to see, but there's a negative on the x. So that means we have a reflection. It's going to reflect from right to left because your positive x's are now negative x's and vice versa. So that means we have exponential decay as it's decreasing. The domain is still all real numbers, and the range is still, your y-coordinates are still positive. They are greater than 0 because we still have that horizontal asymptote. So the outputs will never become negative. That's interesting. You can plug in a positive or a negative input, but your outputs are only positive. Now you might recall that we have seen in the past some properties of exponents. So for example, if we have 5 to the power of negative 2, what we would do is we would typically say, hey, we can't have a negative exponent, and we would relocate that base into the denominator with a positive exponent, right? And that's what we're seeing here. If we have our base with a negative exponent, we can reformat that problem to be a base that is in fact a fraction like this, where the base of the function is now in the denominator. The base of the exponential form looks like this fraction. So we can go backwards even, right? So here's another little example. What if I had 1/3? Well, you could take that denominator of 3, move it across the division bar, and now it's 3 to the power of negative 1. So we can kind of go back and forth between those two formats, and we'll see an example in a moment. So for our transformations, that's this box here in the middle. What we're looking at is we're using this letter A as a placeholder for either a vertical stretch or shrink. So I'm just using abbreviations here to fit this in this little tiny space. Vertical stretch or shrink. Or you could have a negative A, in which case that's communicating that we have a reflection. Now that will flip it upside down. And so that means we would describe that as being a reflection in the x-axis. Your high points are now beneath the x-axis as low points. B then will be the base of our exponential function. What you see right here is letter C. That's in front of the x. So you might have a negative sign right there. So that would also give us a reflection, if it's negative, of course. So a negative C would tell us to reflect in the y-axis. What we're doing is reflecting it right to left, and that's what you see up here in this sketch. We had a negative on that input, and so positive x's are now negative x's. It's reflecting across that y-axis, so it's reflecting in the x-axis. Lastly, we have the h and the k. We've seen those before as our translations, or the horizontal shift. So the h is representing your horizontal shift, or translation, and k is your vertical shift. However, there's a slight twist with the h. Because we have this negative in front of the h, we always have to think in reverse. So if you see an x minus h, well, it's not really negative. You want to think in your head as if that were the opposite, as if it were a positive h, which means you shift to the right. And if you see an x plus h, you want to think the opposite. You want to think of that as if it were a negative h, which means you're really shifting it to the left. So the h's are tricky because you have to change the sign in your head from how it's printed on the page. The vertical shift will stay as it is. So if it's positive k, it'll go up. If it's negative k, it goes down. All right, so we're going to go through this process of first identifying the parent function, then identifying any reflection or stretch or translation, and then we'll graph some of these here. All right, so what you want to do is, in analyzing the parent function, just determine what is the base, and there's your exponent of x, right? So the base it's a 2. It's not a negative 2. We're separating that negative away. That'll be the value of a. So the base is just 2. So think of it as 2 to the power of x. So that will give us these two critical values, 0, 1. How do I know that? Well, if you plug in a 0, what do you get as an answer? What's 2 to the power of 0? It's an output of 1. Let's plug in a 1. What is 2 to the power of 1? It's just the base. So that's why we call it 1, the base. Don't forget you also have this horizontal asymptote, which is a value of y equals 0. So do we have a reflection? Yeah, we do. It's right there. It's on what we call the A. So that means it's going to reflect it in the x-axis. So now think about that. Reflecting it in the x-axis, meaning that any points that are above are now going to be below because we're reflecting it across that horizontal axis. So what we're doing is we're changing the sign on the y-coordinates. So the x-coordinates stay the same. We negate the y-coordinates. No stretch or shrink. Now for the translation. Here's your h and k. But remember we said with h you have to change the sign. So it looks like an x plus 3, but in your head think of it as a minus 3. That means we're moving it to the left. So I'm going to take my x-coordinates and subtract 3. So 0 minus 3 is a negative 3. 1 minus 3 is a negative 2. Now our value of k is, as you see it, it's a minus 1, so that means we are moving it down one space. So that means take your y-coordinates and decrease them by 1 as we're dropping them down. So we have a y-coordinate of negative 1, decreased by 1, that's a negative 2. We have a y-coordinate of negative 2, that's now a negative 3. And don't forget your horizontal asymptote is also a value of y, and that will also be dropped down, so that's going to be located at negative 1. So let me start off by graphing the parent function, and then we'll graph the results, so you can just kind of see how it has transformed. So here I'll do this in a separate color. here you have the horizontal asymptote at 0, and you have critical values at 0, 1, and 1, 2. Right? So there's your parent function in green, that light green color. And here's the resulting transformation. Horizontal asymptote is at -1. Our two critical points are located at -3, -2, and -2, -3. So here they are, those two. Remember, we reflected this graph upside down. We reflected in the x-axis, so that means the curve is going to look like this. So the left-hand part looks almost horizontal as it's running parallel to that horizontal asymptote, and then the right-hand part drops like so. There will be some y-coordinate, there will be some y-intercept, and we haven't yet learned how to find that if it's not a critical value. So in this particular example, I'm going to skip that. That'll be a topic of a future lesson. But to fill in these other characteristics, our domain is all real numbers. Our range describes the y-coordinates. We don't have any positive y-coordinates. We don't even have a y-coordinate 0. We don't even have a y-coordinate -1. They're all underneath -1. So that means we could go from -infinity to -1, but not including -1. So rounded bracket here, not the square bracket. And then, of course, we have the horizontal asymptote at y equals -1. So that's the basics of what we're looking at here, doing these graphing with transformations. Let's look at two more examples just to show some variation in what we might encounter. Here's example number 2. The base is 3. Right? So we start off with the parent function, 3 to the power of x. We set up our critical values, which is always 0, 1, and then 1, the base, which is 3. Again, if you're not sure, you can take that 1 and plug it in. 3 to the power of 1 is just 3. Don't forget your horizontal asymptote. That's y equals 0. Do we have a reflection? It's really tiny. It's easy to miss, but yes, we do. Right there, we do have a reflection. Notice it is on the x. So that means we change the signs on our x. What's happening then is your positive x's are flipping over to become negatives. That means you're reflecting across the y-axis. We describe it as reflecting in the y-axis, but what's happening is our positive x's are now negatives and vice versa. So look at these two examples. These are going to help you with your reflection. If the negative sign is on the x, you're changing the signs on the x. If your negative sign is not with the x, like we saw in example 1, then we're not changing the signs on x's, we're changing the signs on the y's. Here's our critical values then as we change the signs on the x. Y's stay the same. Again, no stretch or shrink in this case. Lastly, we have a translation. There's no value of h. Remember, we saw h right here as in within the exponential field. This plus 2 is not in the exponential field. It's sort of on the main line of text. So that's a value of k. So k equals 2, which means we're going up to, which means our y coordinates will be increased by 2. So the x coordinates stay the same from the previous step on the column. Let's add 2 to each of the y coordinates. So 1 plus 2 is now 3, and 3 plus 2 is now 5. And don't forget your horizontal asymptote is also a value of y, and we add 2 to 0 and get a location of 2. So again, here is our parent function with a horizontal asymptote at 0, and with critical points at 0, 1, and 1, 3. It would be an increasing function like this. But now, we've moved it up to, so the horizontal asymptote is here at positive 2, and our two critical points, in this case we do have a y-intercept at 0, 3. So it's a decreasing function in the right-hand side. It looks like it's running parallel to the horizontal asymptote, but it does decrease very gradually. Our domain is all real numbers. Our range describes the y-coordinates, not equal to 2, but above 2 and increasing above that. Horizontal asymptote is also at 2, and then the y-intercept. Here we do have a y-intercept that came from the critical value, so we can just jot that down and observe that. So these two examples are for the case where you have a negative sign on either next to the base or within the exponential field. So our third and final example, which is at the top of the next page, looks a little bit different in that we have now a vertical stretch. So that's different. And then what's also different is we have this base, which is represented as a fraction 1/4. So remember what we said is we could take that denominator, move it across the division bar, and then it changes the sign on its exponent. So now we have, there's the 2 in front, now we have 4 that's been moved across the division bar. So that means its exponent is now -1, and you still have this x on the outside. And when we use the power to a power rule, we multiply those exponents together. So to just kind of smash them together, we have 2 times the base of 4 to the power of -x. And then there's your +1. So the 2 is my A, right? There's the B, the base. That negative sign that you see there, we had called that the C. And then that +1 is the K. So again, we don't have an H in this case. So my parent function with the base of 4 is 4 to the power of x. Let's set up those critical values. 0, 1, and 1, the base, right? Did you remember that pattern? Here's our horizontal asymptote, which is also 0. Do we have a reflection? In fact, we do. It didn't look like it at the beginning because there were no negative signs in the original format of the problem, but we moved the denominator across the division bar to the top, so now we do have that negative sign and it's paired up with the x. So yes, we will change the sign on our x coordinates. We do have a stretch. This is our value of a, right? That means it's 2 times taller. And if it's 2 times taller, that means we're affecting the height. The height is represented by the y-coordinates. We are doubling the values of the y-coordinates. The x-coordinates stay the same, and the y-coordinates are going to be doubled. So 1 times 2 is 2, and 4 times 2 is 8. Lastly, for the translation, again, we have a value of k, which is 1. We're going up 1. That means our y-coordinates are being increased by 1. X-coordinates stay the same. Add 1 to each of the y-coordinates. And don't forget the horizontal asymptote is now at +1. All right, so again, here's the parent function. The original parent function had a horizontal asymptote at 0 with critical values at 0, 1, and 1, 4. Like this. Right, you can see the bigger the base, the steeper that exponential rate occurs. However, we are graphing this result, so we have a horizontal asymptote at +1. Zero, 3. Again, we do have a y-intercept in this case, and then -1, 9. Again, we see that reflection occurring across that y-axis. There it is. There's your result. So again, our domain is all real numbers. Our range, 1 to infinity. We do have that horizontal asymptote at 1. And in this case, our critical value did provide us a y-intercept. So there we go.